Hey there, K-8 teachers, and welcome to the show. Today, we're diving into something that, let's be honest, can drive us all a little crazy, teaching decimals. If you've ever felt that frustration when a student just isn't getting it, you are definitely not alone. And the good news is, our source material for this explainer offers a really powerful new way to think about the whole thing. All right, so here's our game plan. First, we're going to put a name to the problem so many of us face in the classroom. Then we'll uncover a really surprising, kind of hidden flaw in how we've all been taught to teach decimals. After that, we'll build a super powerful four-part solution, see how one simple method can totally fix those common errors, and then, and this is the cool part, we'll reveal how all of this is actually a secret bridge to get your students ready for algebra. So let's start with part one, the universal decimal dilemma. I mean, the struggle is so real, right? It's everywhere. And as our source points out, these misunderstandings don't just go away. They can stick with people right into adulthood. Let's kick things off with an absolute classic. Why do so many of our students look at these two numbers and swear that 4.18 is bigger than 4.2? You know their logic, right? It's simple, because 18 is bigger than 2. And look, this isn't just some random mistake. It's a huge red flag. It's a symptom of a much deeper misunderstanding, a crack in the very foundation of how they're seeing numbers. And that brings us to a really fascinating and honestly crucial point from the source material. The problem isn't our students, it's the pedagogy. It turns out there's a fundamental flaw in the way we've traditionally taught this stuff that's actually setting them up to get confused. So, what is that flaw? Well, check this out. It's the fact that we often mix up these two very different ideas, position name and positional value. We treat them like they're the same thing, but they're not at all. The position name, like tens or tenth, it's more like a category, an algebraic idea. Think of it like apples or the X in algebra. But the positional value is the actual number that category stands for, 10 or 0.1. Confusing them is basically like confusing the word apple with an actual physical apple. They're related, but they are not the same thing. So how in the world do we fix this? Well, our source lays out this beautifully clear, unified, and really powerful framework that's built on just 4 core concepts. And this, right here, is the key to unlocking number sense for all numbers, whether they have a decimal point or not. Okay, let's break down these 4 pillars. First, you've got the digit. Easy enough, that's just the symbol itself. Then there's the column's position name, like the tens position. After that, you have its positional value. What does tens actually mean? It means the number 10. And now, here's the absolute game changer, the one that ties it all together, the value of the digit. This is what that digit is truly worth. So for that 3 in our example, its value is 3 times its positional value of 10, which is 30. This 4-part system, it makes everything crystal clear. And this is where the rubber meets the road, because this framework is so powerful in the classroom. It gives us one single unified method for comparing numbers, for adding them, for pretty much everything. It just demolishes those common errors we see day in and day out. So check out the method. All you do is compare the true value of each digit, going from left to right until you find a difference. So let's go back to our original problem, 4.18 versus 4.2. Okay, the units position, that's a tie. The value of the 4 is 4 in both numbers. But then we move to the tenths position. In 4.2, the value of that 2 is 0.2. In 4.18, the value of the 1 is 0.1. And we stop right there. Since 0.2 is greater than 0.1, that means 4.2 is the bigger number. The 8 way over in the hundreds place, it literally doesn't matter. This method just works every single time. And what about adding and subtracting? We always say line up the decimals, but that's not really the rule. The real rule, the one that never breaks, is that you have to align the digits that have the same position name. You put the units with the units, the tenths with the tenths, the hundreds with the hundreds. And when you do that, guess what? The decimal points just magically fall into line because they always live in that space between the units and the tenths. The decimal alignment is a consequence of doing it right, not the cause. And all of this, it leads to the biggest idea of the day. This framework isn't just some clever little trick for teaching decimals. It's actually foundational preparation for higher-level math. It's the secret bridge to algebra that we can start building for our kids right in elementary and middle school. I mean, this is such a profound insight from the source material. When we teach our students to think of 3/10 as being in the tenths category, kind of like 3t, we're basically teaching them pre-algebra without them even knowing it.
They learn that, hey, you can add 3/10 and 2/10 to get 5/10, just like you can add 3x and 2x to get 5x. But you can't just add 3/10 and 200ths directly, just like you can't simplify 3x plus 2y. It shows them that the deep down logic of arithmetic and algebra, it's exactly the same.
So, what's the ultimate result of all this? It's one coherent number system. We stop having one set of rules for whole numbers and another confusing set of rules for decimals. Instead, we have one beautiful logical system where the same four concepts apply to every single number. Period. And that leaves us with one final thought to chew on. This whole framework shows that the deep logical structures of algebra aren't some new scary thing that shows up in middle school. They're already there, hiding in plain sight inside elementary arithmetic. So the big question for all of us is this. If this connection has been right under our noses the whole time, what other powerful bridges between mathematical ideas might we be failing to build for our students?